All right, everybody, welcome to week 4 of Introduction to Python. And this week we're going to be covering an incredibly popular Python package called Pandas. So I'm going to go ahead and click on the week 4 tutorial, Pandas tutorial, and here we are. This is what it looks like. Pandas is an incredibly powerful and popular Python package. Why? Because this is pretty much the one-stop shop for most things data science related. You can do all basic data science you can be done with Pandas, and you can even dive in a little bit more into some more advanced data science just with this package alone. So this is a higher level package. It's built on top of packages that we've already covered like NumPy and Matplotlib. So this is a higher level package that has the foundation of a lot of other ones. Pandas is excellent at data science. It's great for time series. It can do matrices. It can do data frames. A good way to think of Pandas is to just imagine anything that Microsoft Excel can do, Pandas can do way faster and a lot more in a lot more intuitive manner as well. So it's just more intuitive. And another way to think about this too, for those of you who took R with me for the first phase of this course, an R data frame is very similar to the structure of a Pandas data frame. So Pandas also does data frames, and these are much, and for those of you who might not have taken that, they're a lot like Microsoft Excel spreadsheets. So Pandas is great for spreadsheets, great for data frames, time series. You can even do some two-dimensional matrices and that kind of thing as well. So it's really good for data science and good for tables especially. So before we go any further, let's just make sure that I have Pandas installed. I'm going to come down here. I'm going to open up Anaconda that I had preloaded. I'm going to go over and click on the environment that we've been working in, Geog 3.8. And now that we're there, I'm going to launch Spider and then Spider. And go back over here. And we are under our package Geog 3.8, and we are under the installed. So these are all the packages we have installed, and I'm going to type in Pandas. And sure enough, there it is. We already had it installed. And the reason being is it's actually a dependency of Xarray. So just like what we did last week with Xarray, Pandas is another high-performance data structure and data analysis tool. And it's just similar to Xarray, but does more so with time series and data tables. It's really a data table piece of packaging there. Come back over here to Spider, and real quick, I just want to see if I can at all change this. Go over to Appearance. Oh, there we go. I'll do we'll do solarized light today. Apply. Might make it a little bit easier for everybody else to see. This feature of Spider, you can change your preferences and change your appearance to whatever you want. So that looks good. And now I'm just going to see. Yeah, there we go. Now I can zoom in, and that all looks good. Cool. All right, so I'm going to pop open a new file here. Close week 1, don't really need it anymore, and here we are right here. So we already saw that we have Pandas installed. So let's just go ahead, and we know we're going to need to import it. So let's import Pandas as PD. And then run that line. And notice that when I change my color scheme, this white button changed to a black button, but they do the same thing. So it just runs out line by line. So now if I do PD dot and hit tab, I have all of these different options, all of these different functions, and that's all because I read in pandas as PD. So this is just a little shortcut to telling Python I want to use a function from pandas. So we come back here, and I just have some definitions up here. These are just some different things that, like, some different functions that pandas offers that are good to know about. And for example, you have all of these different ways of importing different data types: CSVs, tables, Excel files, SQL tables, JSON files, so on and so forth. You can export or save pandas data frame to any one of those files. You can create blank data frames or blank time series. You can inspect data, very similar to just kind of summary statistics in R. You can select different columns of data, select indexes, which is very nice, and you can clean the data, which is really good for quality control and assurance. And if you're ever just doing some data manipulation or just trying to get rid of bad data or adjust values. And what I mean by that is there's actually interpolations that you can do to gloss over NAs and that kind of thing that are really useful in pandas from time to time. You can also sort and group by in pandas, which is really nice. You can join and combine different data frames or different columns. You can concatenate different columns together, join them, and then you have all these other statistics right here. These are just good to know about so that you know kind of the different functionality that pandas offers. And this can be really important because we don't have time to cover each and every one of these. We'll cover most of these and then some, and some ones that might not be listed, but it's just really good to know that they exist and are there. Now we come down here, and let's actually get started with the coding portion of this tutorial. And what we're going to be doing here for this first little section is we're going to play with some data that is resting online. We're not going to download this data at all. And if I click this link open, this is Chipotle orders that is hosted on GitHub right now. But this is just a raw file. It's a raw table. And so what I'm going to do is I'm just going to open that using the read table function from pandas. Copy this over. Run that, and it ran successfully. And now, if we print out orders, this is what it looks like. We have 4,622 rows by 5 columns. And if I want to see my columns, orders.columns, we have order ID, quantity, item name, choice description, item price, etc. And if I run a type, let's say, what kind of type is orders? It's a pandas data frame. So exactly what we wanted to. So that table just was read immediately into a data frame, and that's a good way to think of data frames. They're just tables or Excel spreadsheets or R data frames. We can run ahead on orders. Just print out the first couple lines, and we're definitely constraining. We're not able to see everything that we need to see here. So I'm not sure if there's a way that we can just change the view settings, because that function should be printing out everything that we need there. So that could just be a function of our view, but if we can print out any of these columns that we want. So if we do orders.orderID, there's that column, orders.quantity, there's that column, item name, item price. So we can just print it out column by column like that, just to get an idea, just to get a feel for the data there, because it wasn't quite working. And then, so that is one way to query a column that I was just doing right there, just messing around, is using the dot operator. So we're saying orders.item price. And because that column has a name, item price, it's queryable. The other way to open up a column or to view a column is to use the bracket and refer to the column by name as a character string. Same thing. So notice the syntax here, dot item price or bracket apostrophe item price. Both do the same thing. And then the other thing that you can do that's really nice is you can index from there. So let's say we just wanted the first 5 rows of item name. There we go. So we just appended that bracket where we said, okay, I want this column right here, which if I do .dim, oops, wonder if I can do .shape. It's a tuple, so I can't do that way. But anyway, if I just type in item name right here, tell me that there's no other columns. It's only one column and then an index, and has the length of 4622. So we know that there is only one way to index it, and that is by row. So if I come back up here, that is why there's no commas here. I just want rows 0 to 5. There we go. Same thing can be done the other way too. If we're using the object-oriented way, where we say, okay, orders.itemName is an object, and I want to grab the 0 to 5, the first 5 rows from that, just using the dot operator as opposed to calling it using the bracket. You can do it that way as well. So, and this is a little bit more information on this. So bracket notation like this will always work. Dot notation has limitations. This is dot notation. So dot notation does not work if there are spaces in the name. What I mean by that is if this underscore wasn't here and we just had item space name, the dot notation would not work. Dot notation doesn't work if the series has the same name as the data frame or attribute. So if, for example, we had something like one of the functions that we ran is orders.head. Well, if head is the name of one of these columns, the dot operator will not work, the dot notation. And dot notation cannot be used to define the name of a new series like we do in here. So that was Chipotle, and that was just a quick example of running through that. Let's open up a new data set, a new data table that is also online about UFOs. So again, this is just a raw data set, a data table that's online, and this is actually a CSV file. So we're going to use the read CSV function. How do I know it's a CSV file? If we come up here, so that was just a bit.ly link, but that expands out to ufo.csv. So this is the raw file. So it's a CSV file. So we have our read.csv function, and we run that line. And now we have a UFO data frame, which is 18,000 rows by 5 columns. And now I think because I made this a little bit wider, this is This is using the head function properly and actually showing us all of these different column names. We have city, colors reported, shape reported, state, and we have a date time column as well. And we have these column names right here: city, colors reported, shape reported, state, time, so on and so forth. But what we really want to do is we want to replace these. And so one of the rules that we talked about up here is that dot notation doesn't work if there are spaces in the name of the column. Well, there's spaces right here: colors reported and shape reported. So we want to replace these names. The way that we're going to replace that is using the rename function. We're going to say we're going to rename these columns, and we want to plug them in directly in place. In other words, we want to overwrite those column names. So I'm going to come over here, go below UFO, and notice that this is a dictionary because we are converting these keys to these values. That is just how this particular function works. And so if you're ever confused about that, UFO.rename we said, okay, we want to rename the columns, and then it is a function where a dictionary of values must be unique. Labels must be contained in a dictionary, will be left as is. So we need to use this dictionary, which remember is the curly bracket. And so all we're doing in the dictionary is we're saying, okay, this is our word, this is our definition, this is our key, this is our value, this is what we want to change, this is what we're changing it to. So now if I go ahead and run this, and then I print out UFO.columns, colors underscore reported, shape underscore reported, state and time. Now we say we want to replace all of the column names by overwriting the columns attribute. So this is kind of the way to just do it if you have a super large data set where, maybe you have upwards of 20 different columns and you just want to change a couple. This is the most efficient way to do that. Let's say you just wanted to change them all. The way that you would do that is you would just say, okay, I'm going to make a list here, and the list has to be in the same order. This is a very key thing. It has to be in the same order. So we have our UFO columns right here. So we have city, colors reported, state, and time. And let's just say we want to change that to this. So what we're going to say is, okay, so this is our list, UFO underscore calls. And then we want to say UFO columns is going to equal that list. Because it's the same length, it will just replace our column names like that. So now we have lowercase city, and then we have these spaces again, which we need to get rid of. Lowercase date and time. And I just wanted to show you that that was possible. The other thing that we can do is straight off the bat, let's say we know we're going to be reading in a file, and we know that the column names are bad already. So what we're going to do is we're going to say, okay, we are going to give you the names right away. So we're going to name these columns right away. So we're going to reread in our CSV. So we're going to replace UFO. We're going to reread it in up here. And I'm giving it the names of UFO calls right here. So this is not perfect. This is not a set in stone thing because obviously we still have some spaces down here and this isn't exactly our final form. But I just wanted to show you that this is possible. Now we know that we have these spaces down here. We know that that's not good. So here's a different way, once again, to replace them. And what we're going to do is we're going to say, okay, we want our UFO columns, and we're going to use this fancy function on the end of that where it's string.replace. We're going to replace spaces with underscores. So if there's a space in the string, remember this is a string characterized by the apostrophes right there, we're going to replace that space with an underscore. So simple as that. So this is how the function works. So now, if I go ahead and I come down here and I run this, now my UFO columns finally have these underscores, like once again, just like that. And so this is just another way. And so the reason I'm showing you all this is because even within Pandas, Pandas is such a do-it-all package. There's so many different functions within Pandas that there's different ways, multiple different ways, even within the same package to do something, to accomplish something. So now when we run UFO.head again, just to print out the first couple lines, the column names are appropriate, they look good. And let's say we want to create a new column. in here, and we just want to make it location. So we're tired of city and state being separate. We want to combine those. So if you want to add a new column, all you have to do is use the bracket notation, add in whatever you want, and I just named it location. And I'm going to make location the UFO city plus, comma, space, UFO state. And so just so you can see what this looks like, if I add these two columns together with the space, it's just Ithaca, comma, New York, Willingboro, comma, New Jersey. And we're going to just save that as location right here. So when I run that, and then I also run UFO.head once again, now I have location over here too. So that's great. It's exactly what we wanted. We just wanted to create a new column, and now what I can do is I can run a UFO.describe. So this function is very similar to the summary function within R, and it's just a quick description of statistics of the columns of data within UFO. So UFO.describe. And I'm going to come over here and I'm going to comment this out as well. And that comment is simply just create new column with city, comma, space, state, and save that as location. So come down here and run the describe. So here we go. We have a total number of cities as 18,216. The unique cities are 6,476. The most frequent is Seattle, and that frequency is 187. So we have all that, and let's just say what we wanted to do is we wanted to drop a single column, and that the column we wanted to drop is, let's go ahead and let's drop city, and then we're also gonna drop over here state, because we have those as locations now. And axis is going to be equal to 1, and all that means is that we're replacing the column, and we are replacing it with nothing. It's just being removed. So that's how you just drop those two columns. So we can drop city and we can drop state just like that. So that is just a quick introduction to Pandas for a data table and then a CSV file. And now what we're going to do is we're going to pop in and we're going to use a CSV file of meteorological observation data. So the first thing I'm going to do here is comment out load DOS data. And for those of you who don't know, DOS stands for Delaware Environmental Observing System. And DOS is the most concentrated array of professional grade meteorological observation towers. So we were able to get real-time meteorological observations and report them for the state. And so this is what the website looks like, and I actually make these maps in real time. So we have air temperature for the entire state of Delaware and Chester County, Pennsylvania. So there's Newark White Clay. I can come down here, go to Rehoboth Beach Boardwalk, and so we have these flux towers, kind of look like that right in front of there, and they just collect a lot of different meteorological variables such as temperature, dew point, pressure, humidity, rainfall, wind, so on and so forth. So we're going to load in that data. We have one data set that's within our data sets folder, and we're going to play with that data set. So I'm going to come down here and I'm going to copy this over. and I'm going to run that. File not found error. Okay, so there's a problem here, and why does that problem exist? Because dos.csv is not just within my downloads folder. So I need to track this file down. Let's see, open up my Finder, go to downloads, here's my master folder, there's datasets, there's dos.csv. So I'm going to come back over here, remove all this, and I need to use my root path here. So for me, actually I wonder, let's try this just for 1 second. So I'm in downloads, and then I'm in geo 473-673-master. Datasets, dos.csv. Let's just see if this works. All right, that worked for us. So we don't need to use our root absolute path. We can simply just use, okay, Anaconda and Spider just assume, they just assume that I'm over here in my base folder, which is, I can't query it from here, but if I were to actually pull up my terminal right here, users.james. So if I could see that here's my applications, my downloads, my documents. This is like my computer on a Windows machine. So it just assumes that I'm just at the base right here. And if you're ever confused about where the base is, just come up here. And what Spider actually tells you is this is my file right here. It's untitled 0.py. I haven't saved it yet. And it's saved under /users/james/documents/Delaware untitled 0.py. So this is my path. And this right here, users/james, is my root path. And from there, I'm going to go into documents. So imagine where the first place that Spider is going to look to open up a file is just after users James. So it's going to either look in documents or downloads or wherever I tell it. I said, go ahead and go to downloads, then go to the GitHub folder that I downloaded, go into the datasets folder, and then open up dos.csv, and that's why it ran successfully. So first things first, what we're going to do here, I'm going to open this up just a little bit, and let's just say dos.data.head. So we have 5 rows, 9 columns, and remember this is just the head data. In our actual data, we have 182,645 rows and 9 columns. So let's check out what are those columns looking like. Columns. So we have timestamp, air temperature, dew point, wind speed, wind direction, pressure, radiation, wind gust, gauge precipitation. So this is our time series. And this is what it looks like if we were to actually able to see all the data. So this is just our nice data table right here. And the first thing that we're going to do here is we're going to use our overwriting version right here. We're going to replace all of the columns with this dos calls list. So I know that this is the order that all my columns are in, so I need to match that order. So I'm going to create a new column name list. And it's going to be just like that. And so look at this. I'm completely matched up here. Timestamp is the first. Air temperature, dew point, so on and so forth. So all of this list is in order right here. How do I know it's a list, by the way? They're within brackets. So it's within brackets, there are a number of character strings separated by a comma, thus making it a list. If you're ever confused about that, remember, all you have to do is run a type, dos calls, it's a list. I'm going to use that list. I'm going to replace the names of my columns with that list. Just like that, dios underscore data dot columns equals my dios calls list. Run that line. Now dios data looks like this. Timestamp, air, temperature, no spaces, wind gust. And this type of nomenclature and the way that I've organized these variable names is called camel case. And so notice how I have a capital A, lowercase I, lowercase r, capital T, so air, temperature. So that is one way of organizing your names. So again, this is what it looks like. Now let's say what I want to do here is notice over here. So we have all these variables, and we have this thing over here. It's just counting. That is our index. That is our row number. We know this is a time series because this is just meteorological observations with time. So our index really shouldn't be the row number. Our index should really be the timestamp, because that is the row that is discerning all of these different variables from each other. It's just the time at which these observations were recorded. So I come over here, and what I want to do is I'm going to set my index. So I'm going to say, okay, my dios data, pandas data frame, I want to set the index on that, and I want to set it as the timestamp. And in place needs to be true. Why? Because I'm overwriting it. Come over here, set the index, run through that, and now print that out. There's no more index of 0 through 182,000. Now it's this timestamp right here. And we have 2014, April 4th, 2014 to January 1st, 2016. Now we can run a describe on this data set. Run that line. And for each of these variables, now we see our mean air temperature over this time period is 14.1 Celsius. Our standard deviation, the minimum value, the maximum value. Same with dew points, wind gust, gauge precipitation. So the maximum amount of precipitation we ever had at once was 9.65, and this is 5 minutes apart. So this is 5-minute data right here. So we have April 4th at 4:05, April 4th at 4:10, 4:15, so on and so forth. So 5 minutes separated. So we had 9.65 millimeters within a 5-minute period. It's a lot of rain. And by the way, this data is only for one station. So I have all these different stations right here. It's only for one station. I believe it's for the Newark, the University of Delaware Agriculture Farm. So what I can do now that my index is based on the time is I can check out the location of the data when the index is 2015 is November 29th, 2015 at 23:45. So notice that it's the same format right here. So I have year, month, day, hour, minute, year, month, day, hour, minute, and the dashes and the spaces are the same. And I'm using the dot lock to locate that. So I'm going to come over here, locate November 29th, 2015. Run that, and there we go. Our air temperature for that specific date and time was 7.4 Celsius. Dew point 4.9. So on and so forth. Now I can find out the largest temperatures in this data set. So if I go, there's this fancy function called n largest, and I can say, okay, give me the 5 largest air temperature values, and go ahead and print those out. So if you're looking at a data set like this and you just want to know, okay, let's look at the climatic extremes. Tell me the largest air temperature. So I'm going to grab, so I'm just paste this over here, just grab my column. I want the air temperature column. And then from that column, I want you to grab, using the n largest function, so on that column, dot n largest function, grab the top 5 air temperature values. Come down here and we see that it's all occurred on one day, really within an hour and a half. So all the way up to 37 degrees Celsius, and this occurred on June 18th. Same thing with the smallest. So we see that our smallest air temperature is negative 43.9, negative 51, and these are likely bad values. Actually, they're definitely bad values. That is just not realistic. We are not going to have that large of a temperature decrease within one day, and you would see more April 7th. So you know what that means? The sensor went bad on that day. Could also mean something as similar as there was a bird on that sensor and was hurting the measurements, which can happen time to time. Spider webs and spiders as well. So we look down here, and these are the most realistic ones. So we have negative 16.7, negative 16.6, and this is on February 22nd and 20th of 2015. So those make a little bit more sense. So let's make a series of temperature. So what we're going to do, we're just going to extract just the column air temperature. So we're going to create our own series of air temperature down here. I'm going to run that, and so temp series is only air temperature, and notice that our index stuck with us, so we just have our index and then air temperature right here. And now what we can do is I can organize this, so I can say, okay, grab one day of temperature from temp series. And the way that I'm doing that is I'm using, okay, my temp series is, I'm now overwriting this, is going to be equal to temp series from 2015-06-01 to 2015-06-02. So June 1st to June 2nd, 2015. And the way that I'm doing that is I'm just using this bracket identification. And the reason, normally when we're indexing, we use 0:10, 0:20 if you want the first 20 rows or whatever. But because our index is a date time, we can just query it like so by giving it dates. So I run that, and now we have a temp series, a length of only 288 as opposed to 182,000, and it's only June 1st. So this is just one day, June 1st, 2015. Now that I have that, I can make a figure and plot temp series. And I'm going to use matplotlib.pyplot, and so I read that in as plt up here, matplotlib.pyplot as plt, and I'm going to create a figure that's a size of 7:4, and then I'm going to add my plot to that. So let's go ahead and run, go over to plots, there it is. Now, I created a separate series called temp series for air temperature. The way that I did that was I just called that column into play, and that was all great. It worked out well for just this one series, temp series. But let's say that I can actually do this without creating a new variable. I can do this simply from our original DOS data. So what I'm going to do, copy that over, And now I can create a plot of air temperature and dew point and add all these other fancy aspects to this plot. But look, check this out. I'm doing this for the same day, only instead of using temp series, I'm using Dios data, bracket air temperature, bracket June 1st, 2015 until June 2nd, 2015. And then I'm running the dot plot function on top of that. So this is a lot to unpack here, but basically I can make a single plot just from this one line. So I'm just going to run this one line down here. And boom, there we go. Same exact plot. And this is because there are built-in plot functions within Pandas. So Pandas is built, as I said before, it's built on matplotlib. So we can just use this dot plot function right here and give it a fig size, boom, right there, as opposed to doing it this way where we have plot figure, give it a fig size, and so on and so forth. Same thing with dew point. I'm just querying it the same way. I'm grabbing the same time, then I'm adding a dot plot. So I'm saying, okay, I want to plot, here's my color, here's some of my specifications, and then you can add X labels, Y labels, and titles all to that, legends, all to the same plotting instance. So what I'm going to do is just going to highlight all that and run all that. I don't need this top plot figure. Remove that. And boom, there we go. There's dew point and air temperature for this day, which is just June 1st, 2015. So the x-axis is a little bit ugly. We know it's a timestamp, but the timestamps are overlapping, and there are other ways you can actually go about doing this. They're beyond the scope of the time we have here, but if you wanted to go ahead and go forth that, feel free. It's not super hard, but it's a little bit weird. It's a little bit too far beyond the scope of this tutorial. But we have our temperature Celsius over here, and we know we have just one day, and that is Dios data on June 1st, 2015. And here's our legend right here, air temperature and dew point, so on and so forth. So using this data set that we just read in here, let's go ahead, and this is our Pandas assignment. And so for October 2015, we want to make a wind plot. So we're going to subset the data set to October 2015. So as opposed to one day, we just want 1 month, and that is October 2015. We want to convert wind speed and wind gust data from meters per second to miles per hour. So the only way that I do that is I just say meters per second to miles per hour, and it gives me, okay, 1 meters per second equals 2.23694 miles per hour. So it's just a multiplication, so I just need to multiply my column. Plot the wind speed and wind gust on the same plot. Wind speed as lines and wind gust as points. So same plot as this, only with wind speed and wind gust. Add the legend just like we did, and then compute the correlation coefficient between wind gust and wind speed and add it to the title of your plot. And we're going to use the pandas.dataframe.core function. And so the way that works is diosdata.core. And there you go. So that's basically all you need to know. And then once you get that plot done, just submit it to Canvas.